dropped my notes yesterday and lost everything. All right. All right, let's go ahead and get started. So, first of all, happy Friday. You guys know what today is, right? Today's the end of week 8, meaning that you are halfway through the 16-week semester. So that's exciting news in and of itself. You guys are doing great. Hang in there. We have a lot more to go through in the class, but it's the fun stuff, I promise. You're through the boring part of the class. All right. See how gullible you are. All right. Let's go ahead and get started. So on Wednesday, we talked about blood pressure on Wednesday. And we had talked about the differences in anatomy between arteries and veins. Specifically, we said, arteries have this thicker tunica media, this smooth muscle layer that does a couple of things. One of the things that it does is it enables them to kind of withstand the higher pressure that we find in arteries. But the other thing that it does is it allows us to control the diameter or the radius of our arteries. Our arteries that are carrying blood away from the heart are the ones that are responsible for directing blood flow to different organs, right? So when you're exercising, for instance, you're sending more blood to your skeletal muscles. When you're digesting a meal, you're sending more blood to your digestive organs and so forth, right? So not every organ receives the exact same amount of blood all the time. We're definitely sort of shifting where our blood goes depending on need of a particular organ. And we do that by this process of vasoconstriction and vasodilation. Okay. Another thing that we said is, kind of related to this, is that the diameter of a blood vessel matters, because as these blood vessels get smaller, either through vasoconstriction or whether they get smaller naturally, as we transition from our really large arteries to our smaller arteries, to our arterioles, to our capillaries, what happens to resistance? Increases considerably, right? Remember in Poiseuille's law, we saw the radius was raised to the 4th power. Again, we're not really focused so much on the math here, but I want to make sure that that's underlined, because raising a variable to the 4th power increases its influence on a relationship a lot, right? So a small change in radius can cause a huge change in resistance. That's essentially what that's saying, right? So what that did in our graph that you guys have in your notes on Friday is we saw that when we get to our arterioles and our capillaries, our blood pressure diminishes greatly, right? So we're looking at a venous blood pressure of around, maybe 20 millimeters of mercury. Okay. My question for you guys: what problem does that create? What problem does that create? I thought we would start with a math problem today. Don't worry, it's easy. If I can do it, you can do it. But let's start with a math problem this morning, because years ago I was thinking about this problem, okay, of a low blood pressure in the venous circulation. And I was thinking a little bit about giraffes, because giraffes have a special anatomy, kind of unlike other animals, right? Giraffes have a really long neck, right? If you make fun of my giraffe, I'm gonna fail you in the class. I'm just kidding, I'm not gonna do that. But I'm definitely gonna make you draw a giraffe on the exam, and you're gonna have to, and I'm gonna make fun of it if you make fun of mine. So there's our giraffe's head, and then we've got this little snout right here. There's his eye, right? That's not too bad. I've drawn worse giraffes in my life. All right, so there we go. He's kind of short He's like a, what are they called? Like a miniature giraffe. Right? This is what you might get at your 8-year-old's birthday party. All right, but at any rate, there's our giraffe. His neck could be longer, and his and his belly could be less paunchy. But nevertheless, we got a giraffe. Okay, use your imagination. We got a giraffe. Okay. Pretend that he's really tall and skinny though, like the ones that you see at the zoo. All right. So our giraffe. Heart is right about there. I'll go ahead and do that. Don't tell us another faculty member in the life science department that I drew a heart like this either, because we all know that they don't look like that. All right, so our giraffe, he's about, believe it or not, he's about 20 feet tall. It doesn't look like it from this drawing, but that's all right. Okay, so about 20 feet tall. Okay, 20 feet is roughly 6 meters tall. We'll just go ahead and round it to 6 meters. The heart is about 8 meters off the ground. Okay, so if we were to kind of draw that and map that, that's about 8 meters off the ground. And then, or I'm sorry, 8 feet, sorry, 8 feet off the ground. Now we're about 2.3 meters. Okay, and then we have another 12 feet to go then to the animal's brain, right? Because his brain is sitting up here like this. Okay. Now we said the other day, there's his brain. Not even going to try to make that anatomically correct. So we've got this, right? So we've got about another 12 feet or about 3.7 meters up to here, right? So this is about 12 feet. There we go. So 3.7 meters, all right? So the other day we were talking a little bit about blood pressure, and we were talking about how if your blood pressure is too low, what can happen if your blood pressure is too low? Let's say that you're lying down and you go to get up. What's going to happen? It's going to cause a faint, right? You're going to have that blood drop out of those carotid arteries. Even though your heart rate's going to increase to compensate for that, and we looked at that as well this last week, even though your heart rate's going to increase to compensate for that, we're going to see that you're going to have a faint, right? Because of gravity, right? Your heart is here, your brain is here, and gravity's going to pull that blood down. Well, with a giraffe, we're now looking at a situation where gravity is amplified, right? We're looking at a situation where we've got a very, very long neck, and we have not to raise that blood this far, we've got to raise that blood all the way up to that giraffe's brain, right? 12 feet roughly is what we have to raise that blood. So one day I got to thinking, what does a giraffe's blood pressure have to be in order to make sure that it gets enough blood to its brain? Okay, let's figure it out. Okay, let's make a guess anyway. All right, so we have to know one thing, and I'll give you, well, I have to know two things, and I'll give you a couple of a little bit of information here. So not only do we have to get the blood from the heart to the brain, okay? One thing that we have to do is once we get the blood here, we have to have enough pressure left over to get it through the brain, right? So that it can come back down to the heart, right? So in other words, it can't be just enough to get the blood up to here. It's got to be just a little bit more, okay? I had to look that one up. I didn't know how much blood pressure it took to actually drive the blood through an organ like a brain. So I looked it up, and it turns out that we need about 60 millimeters of mercury left over, okay? So about 60 millimeters of mercury. So whatever value we calculate, we're going to have to add 60 millimeters of mercury to that to be able to get that blood through the brain, okay? Otherwise, calculating blood pressure is actually fairly straightforward, or at least kind of making a guess at it is fairly straightforward, right? So I'm going to give you a little bit of information here, and I'm going to ask you to try to figure out how much blood pressure we need to drive the blood from the giraffe's heart all the way up to the giraffe's brain. Okay? To raise a column of fluid 10 meters, okay? I'm just going to use water, but in this case it's blood. To raise a column of fluid 10 meters, we need an atmosphere, or we need 1 atmosphere of pressure. Okay? So to raise a column of fluid 10 meters, okay, we need 1 atmosphere of pressure. That's actually how we define an atmosphere of pressure, is to raise a column of fluid 10 meters. Okay? 1 atmosphere, and 1 atmosphere is equal to 760 millimeters of mercury. Okay? So, I'm going to ask you guys, how much blood pressure do we need to be able to drive the blood from the giraffe's heart 3.7 meters to the giraffe's brain? Take a minute and see if you can figure that one out. Again, I'm giving you easy math. I know that we don't like it in here, but we're gonna try it. How much pressure do we need to drive that blood from the giraffe's heart to the giraffe's brain? Okay, let's start working it out too. How many of you got the same thing that I got? Definitely not? All right. So how did I calculate this? So what we did is we know that we know what it takes to raise a column of fluid 10 meters, but I don't have to go that far. I need to go 3.7 meters. So what I did is I divided the two to get a ratio of 0.37. I multiplied that times 760 to get 281.2 millimeters of mercury. So just to raise the column of fluid 3.7 meters, I need 281 millimeters of mercury. And then what I did is I just simply added that 60 that I need as a reserve to that, and I got 341 millimeters of mercury. So this is a rough estimate, okay? This is a rough estimate. You know, it probably isn't entirely correct. It's probably a little bit of an overestimate. But suffice it to say, let's just say that a giraffe needs a systolic blood pressure of 341 millimeters of mercury, right? That would easily kill you, but we have a lot farther that we have to send this blood in a giraffe, okay? So we need a much, much higher blood pressure. Giraffes are really cool, by the way. They have a big heart, for one. One that is actually abnormally sized for their body size. Their heart alone weighs almost 30 pounds. It's a massive organ. And then the other thing that we see is that just like in you and I, giraffes obviously change body positions, especially when they go to get a drink, right? Have you ever watched giraffes go to get a drink? They spread their front legs really wide and drop their neck. But when they do that, all of a sudden now their brain is actually below their heart. What do they do to keep from blowing their brains out with that high blood pressure? Well, they have to adjust, but in the meantime, they have to absorb that pressure with something. So they actually have a network of caverns, essentially, in their skull that absorb all of that blood when they drop their head. It's called a rete mirabile, or a miraculous net in their skull that helps to absorb that blood so while their heart makes the adjustment that's needed. So it's kind of an interesting thing, okay? So anyway, just kind of an example of how you can take just a very small amount of data and make a guess at a physiological variable like blood pressure. All right, let's do a brontosaurus now. I'm just kidding, let's not do that. All right, I bet it's bigger, okay, I bet it's bigger. But let's do me for a minute, all right? Let's do Dr. Russell for a second. So let's go ahead and draw Dr. Russell on the board, and let's see what we can do with that. We'll draw him in underneath all of this so that we don't have to erase. So let's do Dr. Russell really quick. So again, in my grand artistic skills, there we go. I'll give myself some glasses. There we go. There I am. It's accurate, there's no hair. So we've got my heart, somewhere in here, okay? Let's take some measurements. For this, I'm gonna have to get creative.
It looks like a necklace.
It does. It's photos on. Measurement. I'm standing straight. Okay. There we go. So there I am. That's how tall I am. So let's go ahead and measure my height. It turns out that this stick is exactly 1 meter. So that makes life a little bit easier. So I can go ahead and put my thumb right there. All right. I am about 1 meter, 1.9 meters tall. Almost 2 meters, okay? And then the other thing that I want to do is I want to measure how far it is to my heart, right? So I'm going to go ahead and I'm going to stand up against the board right here. I'm going to try to make a measurement here. Put my pin here on my heart, right where my heart is, and I'm just going to kind of, there we go, boop the board. Okay, so there we go, we got that, right? All right, so let's go ahead and measure that height. So we're at a meter, okay? We're at a meter right here. In our highly scientific way of measuring things here. And let's go ahead and round it to 1.4, right? So if my 1.9 meters, here we are, my heart is 1.4 meters off the ground, okay? All right, so let's do the exact same thing, right? We know that we're pumping blood through our systemic circuit, okay? We're pumping blood through our systemic circuit, and that blood is coming all the way down here. What I would like you to calculate now, using the same method that we just did over here, is I would like you to tell me how much blood pressure I need to get my blood from my toes 1.4 meters up to my heart, right? So this is how much pressure do I need to get that blood back to my heart? Let's go ahead and calculate that. We know that to raise a column of fluid 10 meters, we need 760 millimeters of mercury. So I'm going to do basically 760 times 0.14. I got 106.4 millimeters of mercury, right? So Dr. Russell needs 106.4 millimeters of mercury worth of blood pressure to return that blood all the way to his heart. Once it's been pumped out to his toes, he needs to raise it 1.4 meters, and he needs 106 millimeters of mercury to do that. But what's our venous blood pressure? It's way lower than 106, right? It's like 20 millimeters of mercury, right? Look at the graph that we drew on Friday, right? Remember that there is essentially no blood pressure in our venous system, right? So that creates a little bit of a problem, doesn't it? I've got to get that blood back to my heart so that I can maintain cardiac output, okay? But I don't have the pressure to do it. I need 106 millimeters of mercury to pull that blood all the way up here, but I don't have that much pressure. I've only got maybe 20 millimeters of mercury. So how the heck am I going to get that blood all the way back to my heart? I don't know. You guys got to tell me. I don't know. I don't know. All right. Just kidding. I'll tell you. All right. Let's erase the terrible giraffe. I've drawn worse. I've drawn worse. Okay. So venous return. Okay. Absence of venous blood pressure. How do we get blood back to the heart? Right? Because we have to get blood back to the heart, right? We've established that. We've known that since we started studying the circulatory system. And you guys, you guys told me last week that if I want to maintain a cardiac output of, I don't know, 20 liters a minute, how much blood has to be coming back to the heart every minute? Has to be exactly 20, right? It can't be any more or any less than that if I want to maintain a cardiac output of 20 liters per minute, okay? So how are we going to do this? We don't have the pressure to do it. We just established that the blood pressure needed for that does not exist. So how are we going to do it, okay? Turns out that there are three mechanisms that we use to drive blood back to the heart, okay? The first mechanism that we use to drive blood back to the heart is something that we call our skeletal muscle pump. You don't have a heart, but you do have skeletal muscles. Okay, so the skeletal muscle pump. Okay. One of the things that you guys noticed the other day when we were looking at the anatomy of arteries and veins is that the picture that I showed you, the vein had a valve in it, right? I think both of my labs noticed that, right? So those veins, especially our really big veins, they have these valves in them, okay? And valves, as we established on Friday, are going to allow for one-way flow of blood, right? So those valves are oriented in this direction. Let's say, for example, that this is a large vein in my leg, right? So what happens is that our veins tend to be sort of buried in our skeletal muscles. They tend to be, especially these big veins with valves, tend to be buried fairly deep in our skeletal muscles. So what we have is we have skeletal muscles that surround these veins, okay? We have skeletal muscles that surround these veins. And what happens is when you move those skeletal muscles, whether it's simply by walking or sometimes even making small postural adjustments, like just from standing around, what happens is that the skeletal muscles squeeze your veins, okay? The skeletal muscles squeeze the veins. And what that does is it pushes the blood upward in the veins, okay? Remember, the valve is going to prevent it from getting pushed downwards, just like your atrioventricular valves. So when we squeeze the vein, what happens is it pushes the blood upward, okay? We relax, and then we squeeze it again, the blood gets pushed upward. Eventually, it makes its way back to the heart, okay? So in our really big veins, in our legs, in our inferior vena cava, we see that we have these valves that are present. And when we push on those veins, we are able to squeeze blood, and it works its way up towards the heart. Okay. And if we think about it, right, as you start to exercise, cardiac output goes up, right? But as you're exercising, these veins are also squeezed at a faster rate because your skeletal muscles are working, right? So the activity of the pump, as it were, sort of matches your physical activity and works to sort of match cardiac output, okay? So the skeletal muscle pump is one way that we get blood back, especially from our lower extremities, okay? Is we just move and we sort of see this happening, right? When we don't move our lower extremities, we can actually see that blood can pool in the lower limbs. You know, we see this a lot of times when we're sitting for long periods of time. Think about being on a long flight or something like that. Or if you're standing in one place all day, right? There are certain jobs that require us to maybe not move around so much, but just to stand all day long, right? If you've ever been in a situation like that, notice at the end of the day that your feet and your ankles become a little bit more swollen, right? That's because you do have fluid accumulation in your lower extremities because the skeletal muscle pump isn't working like it should, right? So what do we do to alleviate that? One of the best things to do is just go for a walk, right? Make that skeletal muscle pump work, pull that fluid out of your lower extremities, okay? You know, we can sometimes see these valves fail. Occasionally as we age, these valves can fail and we can have accumulation of blood in a certain part of a vein. You know, it's one of the things that we see with things called varicose veins, for instance. Okay. So the skeletal muscle pump is one way in which we move blood back to our heart. Okay. Another way in which we do this is one that we actually talked about on Wednesday. It's called the respiratory pump. Called the respiratory pump. In the respiratory pump, this is what we had talked about related to, you know, we did that EKG exercise where I had you guys do that deep breathing, right? And mark the beginning of inhalation and the beginning of exhalation, right? So that's essentially the respiratory pump at work. So what you're doing is when you inhale, you create that momentary slight vacuum in your thoracic cavity, and the fluid rushes into your thoracic cavity to fill that space. The fluid in your blood vessels rushes in to fill that space. So just simply by inhaling, what you're doing is you're creating that momentary vacuum in your thoracic cavity, and you pull fluid back towards your heart. Okay. Again, this is matched by physical exertion. When you're exercising, you're breathing faster, you're breathing deeper than you normally would be, and you are driving more blood back towards your heart. Okay. So the respiratory pump also works to do this, and again, it's matched by physical activity. And then third and finally, our last way to get blood back to the heart is by is just the sympathetic nervous system. Okay? The sympathetic nervous system how is the sympathetic nervous system? The sympathetic nervous system causes vasoconstriction. Okay. Causes vasoconstriction, and when I squeeze that blood vessel, I push blood back towards my heart. Okay, just squeezing that blood vessel pushes blood back towards my heart. Okay, again, that becomes activated during exercise. So we see that to a large degree, our physical activity is going to match the need of a higher venous return. Okay, so these three things work together to pull blood back towards our heart to make sure that venous return matches cardiac output. Okay. There we go. Well, Dr. Russell, he really needs his blood. So there we go. Yeah.
So are you saying like instances like this where all three of these are activated would be like at areas of very high pressure, or is it just like a constant?
These are always working because you always have to get blood back to your heart, right? So, like even now, just walking around the room, my skeletal muscle pump is doing its job. I'm breathing all the time, so the respiratory pump is always doing its job, right? Because we always have to get blood back to the heart after it's been sent out, right? So it just amplifies when we exercise or something like that. Does that make sense?
Yeah.
Okay. Okay. I mean, even just standing, right? It's not doing its job completely, but even standing, you're making small muscular adjustments to maintain posture. And even that's enough to squeeze your veins a little bit, right? This is why you don't keel over when you've just been standing for a really long period of time. Locking your knees and passing out is something, it's a conversation for a different day. But generally speaking, just standing, you can stand for a really long period of time, and those postural changes that you're making are enough to work the skeletal muscle. Okay. All right. Any questions about that? All right. So I wanted to make sure that we covered this. We talked about blood pressure on Wednesday. I wanted to make sure that we at least got to this today. What I want to do now is I kind of want to change topics just a little bit, and I want to spend just a little bit of time talking about capillaries. We haven't really talked about capillaries a whole lot yet, other than the fact that they exist. So I wanted to kind of talk about that for a couple of minutes. And then we should have kind of wrapped up the lecture material that we have on blood vessels. Obviously today in lab we're going to spend some time going through blood vessel identification and stuff like that. But, I wanted to spend just a little bit of time, the remaining time that we have, talking about capillaries, and then we will kind of transition in lab to blood vessel identification. So our capillaries are our very smallest blood vessels. The very smallest blood vessels that we have. And again, I know on Wednesday I showed you guys that PowerPoint slide in which we compared the anatomy of arteries and veins to each other, where we looked at the different tunics, right? The tunica intima, tunica media, tunica externa, and we compared the differences between arteries and veins. There is a capillary on that slide. We didn't talk a whole lot about it, but let's take a second and look at the anatomy or cross-sectional anatomy of a capillary. Capillaries are about as thin as you can possibly imagine getting. Capillaries consist of a single layer of epithelial cells, or endothelial cells, as we call them in blood vessels, because they're lining something, right? They consist of a single layer of endothelial cells, and they rest on a basement membrane, okay? So that basement membrane of connective tissue is also about as thin as you can possibly get, all right? And that's it. That's all you've got with a capillary. You've got a layer of epithelial cells, and you've got your basement membrane. It's basically like the tunica intima of one of our arteries or veins, okay? The diameter of these guys is really small. The diameter, I believe, is somewhere on the order of about 10 micrometers. Not that that matters to us. I don't expect you to remember that number, but it's small enough that your blood cells have to pass through your capillary single file, okay? So I can't have two blood cells passing through next to each other. They've got to get in line with each other and pass through single file. So we're talking about exceptionally small blood vessels here, all right? So very simple anatomy. We can't make it any thinner than this. we have thin endothelial cells, and we have just the required connective tissue for those endothelial cells to rest on, and we have literally nothing else, okay? So very, very, very thin. You have about 75 trillion cells in your body, okay? Every single one of those cells is no farther than about 1/10 of a millimeter from a capillary, okay? So almost every single cell in your body is in direct contact with the capillary. Wait that to sink in just for a minute. Almost every single cell in your body is in direct contact with the capillary. If it's not in direct contact, it's at most about 1/10 of a millimeter away from a capillary. Okay? 1/10 of a millimeter is really, really, really small. Okay? As a result, you have about 50,000 miles of capillaries in your body. If I could take all of those capillaries out and lay them end to end to end to end, it would be a line of capillaries about 50,000 miles long. That's crazy. That's crazy. Okay. Take it a step farther. If I could take out your capillaries, and I could, your capillary is circular, right? What if I cut it on one side and laid it out flat, right? So where it's a flat sheet instead of a circular thing, okay? If I did that and I created some sort of twisted quilt where I put them all together into one really big sheet, you would have a footprint large enough to cover the footprint of this building as well as the nursing building. That's how much surface area of capillaries you have in your body. One of the things our bodies are really good at are taking really big surface areas and folding them up into a very, very small space. Okay? Are your minds blown yet? Okay, I'm gonna keep trying. I've got 8 more weeks to just utterly and completely blow your mind about your own body. So hopefully if that didn't do it, I'm gonna keep trying, okay? I'm committed to you, okay? The total surface area is about 6,300 square meters, okay? A square meter is about the size of this tabletop up here. 6,300 square meters is what we're looking at. Okay? I can't even afford a house in California that has a floor plan of 6,300 square meters, right? I mean, that's some expensive fucking real estate right there, right? And I've got that inside my body, and it's doing the very best thing that it can possibly do. It's exchanging oxygen and nutrients with every cell in my body, okay? That's craziness, okay? So your capillaries are the site of exchange, okay? This is where we see oxygen and nutrients being exchanged with your cell, because diffusion works wonders when we have a very short distance for things to diffuse across, okay? If your capillaries were any thicker than they are, it wouldn't work, right? If you had 2 layers of epithelial cells, diffusion would be slowed down and it wouldn't work as well. It's got to be as thin as it possibly can be. And we'll talk about that in more detail when we get to the respiratory system in a couple of weeks.
Can you repeat what you said that they do with oxygen and something else that you said?
Nutrients. Okay. So your capillaries, this is a cross section. This capillary is coming out of the board right here. Okay. Your capillaries, though, if we looked at them sort of from a side view, a longitudinal view, we have 2 kinds of capillaries. We have a kind of capillary that we call a continuous capillary. Continuous capillary. And then we also have capillaries called fenestrated capillaries. And with fenestrated capillaries, we see that there are little gaps in the cell membrane. Okay? So we actually have fenestrations in the cell membrane. And what those fenestrations do, as you probably can guess, is they allow for really large amounts of materials to cross across, right? Rather than just simply relying on diffusion across the cell membrane, now we actually have openings that allow for really large amounts of material to cross the cell membrane, okay? So fenestrated capillaries are found in organs where we have large amounts of exchange occurring. Okay? How to study capillaries? There's two main places in our body we find them. We find them in our digestive organs, digestive tract, and we find them in our kidneys. Okay, pretty much the rest of your body has continuous capillaries, right? With no big fenestrations in them, right? So what we're doing is we're relying on diffusion for exchange to occur, right? So this would be diffusion. We're relying on diffusion for exchange to occur. Continuous capillaries, we see that in most tissues, there are leaky junctions between cells. So we're relying on diffusion, but there is a little bit of leakage that takes place between cells. Okay, so there's leaky junctions between the cells, except for one obvious place in our body. Where's the obvious place where we wouldn't have leaky junctions between our cells? You may know. You learned this one. You learned it in 50A. Where's the one place where we really try to limit what gets exchanged across capillaries? Where? The brain, yeah, the central nervous system, right? You guys have something in your central nervous system called your blood-brain barrier, right? That blood-brain barrier is in place partly because between the endothelial cells we have tight junctions, right? Except for the blood-brain barrier. And between those cells we have tight junctions. That's the one place in our body where we aren't just allowing all sorts of stuff willy-nilly to occur. We have tight junctions. Okay. So capillaries are super cool blood vessels where we see just a lot of exchange happening, right? It's the one place in our body where we allow for a lot of, I guess, leakiness, as it were. Okay. That leakiness comes at a slight cost, and we need to talk about that too. So, I'll let you guys finish these up and erase over here. Okay, let's go ahead and draw a capillary on the board. We're going to make it kind of big. So there's a capillary, okay? And through your capillaries, all 50,000 miles of them, you have about 7,200 liters of blood every single day that flow through your capillaries. Okay? So that's a lot of blood. Okay, about 7,200 liters every single day. Flowing through your capillaries. Okay? All right. What did we say happens to our blood pressure as our blood flows through our capillaries? Does it increase or does it decrease? Decreases, right? Okay. So we're going to go ahead. What I would like to do is I'd like to actually write down the pressure in your capillaries. Okay. So blood pressure in your capillaries is P cap. When your blood enters your capillaries, it's already decreased a lot because of your arterioles. So we're looking at about 32 millimeters of mercury, okay? But as that blood flows through your capillaries, the pressure decreases even more. And by the time we get to the venous end of the capillary, we're looking at a pressure of about 20 millimeters of mercury. Okay. Is your blood pressure, is it an outward pressure, like this? Or is it an inward pressure like this? Outward, right? It's an outward pressure, right? So what we see then is that outward pressure is pretty big at this end, or at least relatively big at this end, right? And then by the time we get to this end, that outward pressure is fairly small. Okay. Remember that your capillaries are leaky though, right? So has anybody ever, this is gonna be a random question, but has anybody ever, like at home, have you ever used like a soaker hose in your garden? You just know what soaker hoses are? They look like a regular hose, but they've got all full of holes, right? And so what happens is when you turn them on, water just leaks out of them. Out of the entire length of the hose, water leaks out. So the idea is that you just string the hose through your garden or your flower bed or whatever, you turn it on, and then water just leaks out all along the whole length of the hose, rather than just the end with a regular hose, right? Your capillaries are like a big soaker hose, right? So this blood pressure is actually pushing fluid out of your capillaries. Okay? So as fluid flows through as blood flows through your capillaries, you're actually losing a small amount of fluid. So you have about 7,200 liters a day entering. You have less than that actually exiting your capillaries. Okay? Now we can reclaim a little bit of that fluid because we have an opposing force. This is one that we haven't talked about yet, but we're going to start talking about it more and more and more because it gets important as the next couple of weeks go on. The other one that I want to talk about is a pressure that I'm going to use the Greek letter pi to abbreviate. And I'm going to use the subscript capillary just to denote that it's in their capillaries. Okay? This is what we call the colloid osmotic pressure. Colloid osmotic pressure, okay? Oh no, osmosis, it's back, okay? We thought we escaped it in early 50A, but it's back. What is osmosis? The diffusion of water. What's it caused by? It's caused by a concentration gradient, right? It's caused by stuff in the solution, right? What stuff are we dealing with here? Well, your blood has stuff in it, okay? I'm going to say this like 5 times because I want it in your notes underlined at the top of the page. In your blood, the most common solute, the most prevalent solute in your blood are proteins, plasma proteins, okay? Plasma proteins are the most prevalent solute in your blood. Plasma proteins are the most prevalent solute in your blood. Plasma proteins are the most prevalent solute in your blood. Plasma proteins are the most prevalent solute in your blood. All right, I see everybody writing it. Made it. Okay, so plasma proteins are the most prevalent solute in your blood. I'm going to get tattooed on my forehead is what I'm going to do. All right? Plasma proteins are the most prevalent solute in your blood. All right? Why is this important? Well, most of those proteins are pretty big. Okay, we'll talk a little bit more about them next week when we talk about blood, right? But most of those proteins are pretty big. So while our capillaries are like the mecca for diffusion, those proteins can't really diffuse out of our blood. They're too big to cross the capillary membrane. In fact, if they do start crossing our capillary membrane, we got problems, and we'll talk about that later on in the semester as well, right? So those proteins, even though we're losing fluid, we tend to keep those proteins here in our blood. And what that does is it actually creates an osmotic gradient, and it tries to pull fluid into the bloodstream, right? So while the blood pressure is pushing out, our colloid osmotic pressure is actually pulling fluid in. Okay? So cap, it's equal to about 25 millimeters of mercury. Okay? And what that's doing, again, is it's actually pulling fluid into our blood. Okay? So while our blood pressure is pushing fluid out, our colloid osmotic pressure is pulling fluid in. Okay? Think of it like a tug of war, right? The fluid pressure, the blood pressure, is trying to pull fluid in this direction out of the capillary, and the colloid's osmotic pressure is pulling fluid in this direction, right? So it's like a big tug of war that they have going on. Okay? Colloid osmotic pressure remains relatively unchanged. Okay? So, at both the arterial end and the venous end of our capillary, we're looking at a colloid osmotic pressure of about 25 millimeters of mercury. Okay. You guys with me so far? All right, just a tiny bit more math, and then I promise I'm done for the day. Okay? Didn't know you were going to get into that today. All right, let me ask you a question. At the arterial end of the capillary, at this end of the capillary, which one is bigger? Blood pressure is bigger, right? So at the arterial end of the capillary, we end up with a net loss of fluid, right? In fact, it turns out to be a net loss of about 7 millimeters of mercury. Okay. At the venous end of the capillary, the story is different. We've had a decrease in blood pressure, while colloid osmotic pressure has remained the same. So which one is bigger at this end? Colloid osmotic pressure. Cool. So we have a net gain of fluid at that end of the capillary. Does the net loss equal the net gain? It does not, right? So even though we've regained a little bit of fluid, the story remains kind of the same. We still have lost a little bit of fluid in our capillary. It's a really small amount, okay? Of the 7,200 liters of fluid entering your capillaries a day, your net loss is only about 3 liters, okay? Net loss is only about 3 liters, okay? And that's a really small percentage of the 7,200 liters that go in a day, but it's still a net loss, okay? So I'm gonna ask you one final time today. If I want to maintain a cardiac output of X liters per minute, you can fill in whatever number you like, how much blood do I have to have coming back to my heart a minute? Has to be the same amount, right? Has to be exactly the same amount. I'm losing a tiny amount of fluid in my capillaries. So how am I going to make sure that the fluid is the same amount? How am I going to get that very small amount of fluid back? Turns out that I have an entirely separate circulatory system devoted to just this. This is my lymphatic system, okay? So I have another set of vessels, another set of capillaries that we haven't even talked about yet, called my lymphatic system. You have lymphatic capillaries, you have lymphatic vessels, and this fluid that's lost becomes lymph, okay? And that lymph is sent back to your heart via a completely separate and completely autonomous circulatory system. On the way, you send that lymph through lymph nodes, right? There's a high concentration of white blood cells in those lymph nodes, so you're monitoring it for potential pathogens and things like that. But this net loss becomes lymph. And your lymphatic system comes into play. Okay? We don't have really a whole lot of time to talk about your lymphatic system in this class. I wish we did. It's kind of an interesting one. But we do have an entirely different circulatory system, other than this one, that's responsible for returning that lymph back to our circulatory system. Okay? It actually dumps that lymph in right before the heart, so the numbers end up working out. Okay? And we'll come back to the lymph system just a tiny bit. Ironically, when we talk about the digestive system, as we look at some lymphatic stuff. But beyond that, this is a essentially what we have. All right. I'm just going to mention it right now. All right. It's exactly 9 o'clock. I did it. Okay. All right. So what we'll do in lab.